Hello, students. Welcome to Inside Physics. This is Srinivas. So, today we will discuss about black body radiation. Okay, see what is a black body? Before going to that, we will discuss the properties of thermal radiation. What is called thermal radiation? The radiation emitted by a body by virtue of its temperature. How a body gets temperature? When we heat a body, it will get temperature and the temperature of the body increases. So when we heat a body, the object will radiate some energy. That is called thermal radiation. This thermal radiation will increase with increase of temperature. So if you give continuous heat, the temperature of the body increases, it will increase the thermal radiation emitted by the object also. Okay. See, thermal radiation for lower temperatures is in infrared region. Infrared is region is invisible, and the radiation, thermal radiation, that means the heat energy, is also in the invisible region. We cannot see the thermal radiation. Okay, so if we continuously heat the body and the temperature is increased, the intensity of thermal radiation will be moving to higher frequencies. The peak of the radiation, the highest intensity, will move towards the higher frequencies. Okay, so the thermal radiation in this way will give all the wavelengths of radiation. So we can say that thermal radiation will emit continuous spectrum. Okay, so if suppose we take an example of a incandescent bulb, a filament bulb. Okay, if we pass through the filament some current, before passing the current, the filament will not glow. After passing the current, the filament will slowly gets heated up. At the beginning it will show some red, orange, yellow, and after passing through continuous current it will further gets heated, and finally it will show white light. So that means with the increase of temperature, the intensity of radiation will increase. Okay, and above 1000 degrees centigrade, an object will emit all kinds of wavelengths in its radiation. Okay, that is why we say thermal radiation will form continuous spectrum. Okay, so here is something about the thermal radiation. Okay, now we see what is a black body. If an object can emit radiation by giving temperature, by giving heat, then it can also absorb the radiation incident on it. Okay, if an object can emit the radiation, it can also absorb the radiation incident on it. A body which can absorb all the radiation incident on it is called a black body. Black body is not actually, doesn't look black. Why it is called a black body means, black color represents actually the absorption of all wavelengths, all colors of wavelengths. So when a body is absorbed all wavelengths of light, it looks like black. Okay, that's why if a body absorbs all the radiation incident on it, it is called a black body. Okay, that is the definition of black body. Generally, a perfect black body is not there. Okay, but an idealized black body, that means a practical black body, can be made by a sphere with some cavity inside. Okay, so a metallic sphere with some cavity inside. Okay, so how that sphere with cavity inside can be considered as a black body, that we will see with the black body cavity diagram. Okay, if we consider a sphere with some cavity, okay, this is a sphere and inside there is a layer of lamp black. Lamp black is generally a chemical agent used in shoe polishes and some shining agents and some cement industry, paper industry. That lamp black is coated inside the sphere. So this lamp black will actually reflect the radiation, and some part of the radiation will be absorbed also. So when an external, see, we put a radiation reflector here. If an incident radiation is incident, sorry, it's not a perfect straight line. Anyway, if it is considered as incident radiation, okay, so this incident radiation will pass through a small hole drilled in the sphere. A small hole is drilled in the sphere and the incident radiation will fall on this, and this will be reflected here, and at this point some light will be reflected and some will be absorbed. See, some part will be reflected back again and some part will be absorbed at the walls of the sphere. Okay, so in this way all the incident radiation inside the sphere will be absorbed and reflected. So some part is absorbed, some part is reflected. This process continuously happens inside the cavity, and finally the total radiation inside the cavity will be absorbed by the sphere. So if we consider, if the total radiation inside the cavity is absorbed, it looks black inside. When we see through the hole drilled into the sphere, the hole looks black because it doesn't have any light to see, because all the radiation is absorbed. It looks black through the drill, through the hole we have drilled into the sphere. So here this can be considered as a perfectly black body, and if a black body can absorb all the radiation, and this has a property of emitting the radiation also. Okay, see, if the cavity is heated, so the radiation intensity will be given out by this sphere. That radiation will be coming out of the aperture. So a good absorber and a good emitter. So a black body is a good absorber and also a good emitter. Okay, so when the incident rays are falling on this inside cavity, the probability of the radiation coming out of this hole is almost zero. That's why when we see through this hole it looks like black. Okay, see, the emitted radiation when we heat this cavity, okay, will be analyzed with we can analyze that radiation with some infrared spectrometer, and the capture of radiation is done with bolometer. Okay, so with some infrared spectrometer, if we analyze the radiation came out of this black body, so we can actually uh, say that the all the wavelengths emitted by the black body radiation will be having some peaks at some wavelengths. Okay, will be having some peaks at some wavelengths of highest peaks, and that if we continuously increasing the temperature of the black body, and the peaks will be also having increased from lower radiation intensity to higher radiation intensity, and they will be also coming to gradually decrease the intensity and gradually coming to zero at very higher wavelengths. Okay, that is actually shown in this graph. Okay, in this graph, if we consider on x-axis the wavelength of the emitted radiation in nanometers and the radiation intensity on y-axis, and if you plot some graphs with 5 different temperatures. Okay, if we see this at 3500 K, see the radiation emitted will be plotted with this graph. There will be a small peak, and the radiation of intensity is also less, between 0 to 200 Kelvin per nanometer. And at 4000 Kelvin, see again the plot, that graph has some peak at radiation intensity peak increased above this plot. In this way, for different temperatures, we have plotted the graphs, and by this we can say that by increasing the temperature of the body, the radiation intensity will be having some highest peaks, and gradually it is coming to zero level at very high wavelengths of radiation. Okay, so a perfect black body is, once again I am repeating, a perfect absorber and a perfect emitter. Okay, so this is the information about black body radiation. So in the next class we will see some useful topics on quantum mechanics.